What's up? I'm Vin, and today I want to go through the June 2023 Geometry Regents, and I'm going to do parts 2, 3, and 4. And first up here, we have the part 2 questions that are worth 2 credits each. For question 25, we have triangle ABC, and we're going to use a compass and straight edge to construct the altitude from point C to side AB. So for this question here, be very careful. I saw a lot of students just construct the perpendicular bisector of side AB. But this is a very dangerous bear trap. That would tell you the midpoint of side AB, which would help you construct the median. But we want the altitude. So that means we're going to start here at point C, and we're going to swing an arc so that it hits this side AB in 2 locations. So I have to open it up a little bit like this, and we're going to swing the arc. So we have 1 point of intersection here, and then we continue this, and we do it on the other side like this, and it hits the side AB in 2 locations. So now what we could do is move the compass to this point of intersection, and we swing an arc like this. And we could imagine when the altitude comes down, it's going to go here. So I need to make sure that I extend this far enough so that I have an intersection point when I construct this next arc. So we move the compass now to the second intersection point, and we're going to swing an arc now going in this direction like this. So we swing the arc, and there's our intersection point. And now we can move our straight edge over like this, and we're going to line it up with point C and this point of intersection that we just made here. So now we just connect. We have point C. We're going to drop down this line segment here like this, and we connect it to this intersection point. And if we notice over here, this intersection point, it made a 90-degree angle to this base here. So we definitely have an altitude here. So this is the altitude of triangle ABC going through point C. Question 26, we have triangles ABC and DEF are graphed on the set of axes below, and we have to describe a sequence of transformations that will map triangle ABC onto triangle DEF. So for this question here, what we could do is we could focus on a single point. Like notice here, point B has to land on top of point E. So if we focus here on point B, it has to land on top of point E. So that tells me that we're going to have to rotate this triangle, because notice that point B is facing up like this. But then when we get to the image, the point that we're trying to get it to point E, it's facing to the right like this. So we're going to have to rotate. Now, me personally, I can't memorize the rules for rotation. So what I like to do is I take my paper and I actually rotate it. And if I were to rotate this paper 90 degrees clockwise, so I'm going to spin it this way like this, just once, I'm going to make a 90-degree turn. I pay attention to where did point B wind up. It went to the point 1, 2, 3, 4, 5, 6, 7, 8, -2. So this is now at the location 8, -2. And if we look over here, we go 1, 2, 3, 4, 5, 6, 7, 8, and then down 2. And sure enough, this maps it directly to point E. But now I'll verify the other points. Notice here that point A is landing in this location where point D is. So now I'm looking over here, point A is going to land here. And let's see where it went. It went 1, 2, 3, 4. So it went to the point 4, 0 like this. So if we look in the diagram, we go 1, 2, 3, 4. And sure enough, point D is mapping to 4, 0. So far, so good. And then the last point to check here would be point C. So point C right now is at 4, 4. But it should land over here at 4. This looks like, yes, 4, -4. So if we look, 1, 2, 3, 4. And then we go down 1, 2, 3, 4. And that'll map. We have point C going to point F. Okay, so that's going to send it down here like this. So the rotation that we're doing is a rotation of 90 degrees clockwise about the origin. Now, before we move on, it's very important that if you want full credit, that you have to state the direction that you're rotating as well as the center of rotation. There's more than one way to get full credit for this question also. Let's say we had rotated 90 degrees clockwise about point C. That would throw the triangle facing this direction. So we'd have 1, 2, 3, 4. So A would essentially map up here. And then B would be in this location. Let's count 1, 2, 3, 4. It would go 1, 2, 3, 4 to this location here. So the triangle, if we rotate 90 degrees clockwise about point C, would be facing the correct direction. But then we would have to translate this going down 1, 2, 3, 4, 5, 6, 7, 8. So once again, there's more than one way to do this, but I personally like to do this in as few steps as possible. Question 27, we have line segment PQ has these endpoints here, and we're told that point R is on line segment PQ, and we have to determine and state the coordinates of R such that the ratio of PR to RQ is 2 to 3. So what I'm looking at here is, I imagine we have this line segment, and I could draw this on the graph, but I personally like to do it off to the side, because if the answer for the coordinates of R was in decimal form, that's going to be really hard to see on a graph. But what we do know is that R is placed in such a way that it breaks this line segment up into a ratio of 2 to 3. So R would be located at this location, because notice I have 2 equal parts to the left of R, and I have 3 equal parts to the right of R. Okay, so that's the concept. But now what I want to think about here is if I'm going from negative 5, 1 all the way to 5, 6, and I'm doing 5 equal jumps, what I'm thinking about is what is my change in x? Well, I'm going from negative 5 to positive 5. So that's a change of 5 minus negative 5 or 10. But once again, I'm doing 5 equal jumps. So that means I'm going to divide this by 5, and I would have 10 divided by 5, which is equal to 2. So now I'm just going to start adding 2, but I'm adding it to the x coordinates. So I do negative 5 plus 2 would give me negative 3, and I'll leave a space for when we find the y values. If I do negative 3 plus 2, that's going to give me, we would have negative 1 and then some mystery y value. If I add 2 again to the x, I get positive 1 and some missing y value. And I do 1 plus 2, I get 3, and I get some missing y value. And then notice here, if I do 3 plus 2, it brings me to 5. So far this is looking good. And now to find what is my change in y, my change in y, I'm going from 1 to 6. So now we focus here. We're going from a y value of 1 to a y value of 6. So ultimately we're going up 5, but we're jumping 1, 2, 3, 4, 5 times. So here I would do 5 divided by 5, which is 1. And now let's see what happens when we start adding 1 to the y value. So 1 plus 1 is 2. We add 1, we get 3. We add 1, we get 4. 5, and then check it out, 5 plus 1 gives us 6. So our solution here, r, would be located at negative 1, 3. But if you want a more direct way of doing this, there are formulas for this. I, once again, can't memorize formulas. So what you can do is you could say x equals, and you write your starting x value like this, negative 5, plus if our ratio is 2 to 3, that means r is located 2/5 along the way from p to q. So I could do plus 2/5 times, and then what is my change in x? I still have to write my change in x here. My change in x, I went from negative 5 to 5. That's a change of 10. And if we simplify this, 10 divided by 5 is 2. 2 times 2 is 4. So I have negative 5 plus 4, which is negative 1. And notice it matches our x value. If I want to find the missing y value, I'm starting at y equals 1. We're going 2/5 along the way, and our change in y, we're going from 1 to 6. So that's a change of 5. 5 divided by 5 is 1, so I would have 1 plus 2, which is equal to 3. So this is a more direct way of finding this. But once again, I like to draw this out because it brings the concept to life. Now, I'm going to use the graph here just to see how reasonable our answer is. But if we plot all of these points that we had before, we could see here that r, located at negative 1, 3, does break this line segment up in such a way that the ratio of PR to RQ is 2 to 3. Question 28, a circle has a radius of 6.4 inches, and we have to determine and state to the nearest square inch the area of the sector whose arc measures 80 degrees. So for this question here, let's just draw out a circle, and we're finding the area of just this part of the circle. So we have a sector here. The measure of the central angle here is 80 degrees. And we know this because if the arc is 80 degrees, the measure of a central angle is equal to the measure of the arc that it intercepts. So now I'm going to label the radius here as 6.4 inches. And what we're finding is the area of just this section here. So we're finding the area of this space. So now let's think about what formula do we need? We need to know the area of a circle is pi r squared. And if you forget this, it's in the back of the test on the reference page. And what we're doing though is to find the area of just the sector is we're going to be taking a fraction of this. We're not going to be taking the whole area because we only want this part. So the area of the sector we could say is equal to, we start off by writing pi times the radius squared. So we have pi times 6.4 squared. But once again, we're only taking a fraction of this. And we have to think about the part here is 80 degrees, but we're going out of the full spin is 360. I don't have to write the degree symbols here because they technically just cancel out like this. So we're taking 80 out of 360 of this total circle here. So now we just have to type this in. So we have pi, that's second and the up arrow here. We have 6.4 squared. So 6.4 in parentheses, and we square it. And then we're going to multiply that by 80 over 360. So I'm just going to put a parenthesis here and say 80 divided by 360. So now once we multiply all of this, our solution here to the nearest whole number is going to be 29. So our solution is 29 square inches, but once again, we don't get graded on our actual units. Now, just to recap real quick, how do we get 29 out of this? Well, to the nearest whole number, the ones place is here. We look to the right and it's a 5. So that tells us to round up. So that's why we're rounding up here to 29, and that's our solution. Question 29, we have a large snowman is made of 3 spherical snowballs with radii of 1 foot, 2 feet, and 3 feet respectively. And we have to determine and state the amount of snow in cubic feet that is used to make the snowman. And we're going to leave our answer in terms of pi. So for this one here, we have to use this formula, volume equals 4/3 pi r cubed. This is the formula for the volume of a sphere. And I know we're using this formula because the snowballs are spherical, and we're finding volume since we're talking about cubic feet. Okay, so here's the snowman over here. So there's the head, there's the, I guess, the mid part here, like his chest and stomach, and then there's his legs down here like this. So what's actually happening is we have the first radius here is equal to 1. So we have a radius of 1. And then the second radius over here is equal to 2. And the third radius is equal to 3. Once again, you are not graded on you using units for these questions, so you can just write it in number form like this. So the amount of snow that we're going to be using, so the amount of snow is equal to, we're going to have the sum of these three volumes. So the first volume would be 4/3 pi times the first radius is 1, and we're raising it to the third power. Plus, then we find the volume of the second sphere. We have 4/3 pi times 2 cubed. And then we have plus 4/3 pi times 3 cubed here like this. Now from this step, if you just know, because our answer has to be in terms of pi, to add up all of this but leave the pi out, then great. Otherwise, if you want to see the concept, you're factoring out a pi essentially. So we want the answer in terms of pi. So I'm going to write it on the outside of the parentheses. So we're going to have pi times, and we would be left with 4/3 times 1 to the third plus 4/3 times 2 to the third plus 4/3 times 3 to the third. So in the calculator, all we're going to be typing here is this part here inside the parentheses, because once again, we want our answer in terms of pi. If we write the pi with it, it's going to give us a decimal. So let's go ahead and do that. We're just going to be writing the stuff inside the parentheses. So we have 4/3 times 1 to the third, and we'll pretend that we don't know 1 to the third power is 1. So we have 1 to the third up here like this, and then we're going to add, we have 4/3 multiplied by 2 to the third power. So now we're going to write 2 to the third power inside here like this. And then we have the last part, we have 4/3 3 to the third. So we have plus 4/3 3 to the third power. So this is the last part here in our sum. So now we just press enter, and this works out to 48. So the stuff inside here simplifies to 48. So we have 48 times pi is 48 pi, and that is the volume of our snowman in cubic feet. Question 30, we have a diagram of right triangle ACB. Altitude CD is drawn to the hypotenuse AB, and we're told AD is 2 units long and AC is 6 units long. We have to determine and state the length of line segment AB. So for this question, the big concept we have to know is that when you have a right triangle and you draw an altitude from the right angle to the hypotenuse, the 3 triangles that you have are all similar, which means we can set up a proportion to solve for some of the missing sides. So there's the altitude rule and the leg rule, and me personally, I can't memorize those rules. So this is my thought process. I think of any one of those triangles are going to be looking something like this. Okay, so they're going to be looking something like this. There's 3 right triangles, and I think of this one here. I'm just going to call this one the short leg. So there's the short leg, there's the long leg, and there's the hypotenuse. Okay, so it's going to be one of those 3. So it's short leg, long leg, hypotenuse. So I think about what we're trying to find is the length of AB. So we could call this piece here, we'll call this entire thing X. So think about what were we told here? Well, 2, if we look at triangle ADC, 2 is clearly the short leg. Okay, so this is the short leg. And 6 in the little triangle over here is the hypotenuse. Okay, so if we're talking about, once again, if we're talking about triangle ADC, this is the short leg, I would say, of triangle ADC. And this is the hypotenuse of, we could say, triangle ADC like this. Okay, so when I set up the ratio 2/6, I'm thinking here in terms of my ratio, I'm doing the short leg, so the short leg over the hypotenuse. Okay, so that's what we're focusing on. And this is, once again, in triangle ADC. Okay, so we're talking about triangle ADC, we're doing the short leg over the hypotenuse. So now when I look at the big triangle, see the big triangle here, I'll highlight this, is triangle ACB. So there's the big triangle. Now when we set up our ratio, we have to make sure that we do short leg over hypotenuse. So what is the short leg of the big triangle? Well, that one is going to be 6. Okay, so that's equal to 6. The short leg is going on top, and the hypotenuse we're calling X. That's what we're trying to find here. So now we just have to solve this proportion for X. And we're going to do 2 times X is equal to 2x, and we have 6 times 6 is equal to 36. So now divide both sides by 2, and that tells us x is equal to 18. But I would just make sure I clearly state this. The length of AB, I'm going to write out AB is equal to 18, and here's our solution. Question 31, we have triangle RST with vertices at these coordinates here, and we need to determine and state the equation of the line parallel to RT and the line has to pass through point S. So for this question here, what I'm thinking about is we have triangle RST, and this is not necessarily drawn to scale. This is just to help us come up with the game plan here. So we have triangle RST, and we want to come up with the equation of the line that's parallel to RT, and the line has to pass through point S. So right away, what I'm thinking here is that since we're coming up with the equation of a parallel line, I know that parallel lines have equal slopes. Okay, so what we're going to be finding here is we need to find the slope of segment RT. That's very important because the line that we're coming up with is going to have the same exact slope. And we're going to use point S to use our equation of a line. So we're going to write the equation of a line. It has to pass through the point 3, 2. So the formula that I'm thinking of ultimately that we're going to have to use is y minus y1 equals m times x minus x1. This is the point slope form equation. And it's very helpful for this question. So first, let's find what is the slope of RT. So the slope formula we're going to use, we have y2 minus y1 divided by x2 minus x1. So now we just plug in the points here. So we're going to be using, once again, RT. So I'm taking the difference of the y values. So we're focusing here first. We're taking the difference of the y values. So I'm going to do -4 minus -2. And then here I'm going to divide by, we focus on the x values next. We're going to have 4 minus -3. Okay, so 4 minus -3. Now, just to make sure that you're neat, you can label this. You could call this x1, y1, and you could call this point here x2, y2. And then you could see how this fits into the formula, the way that we have everything written out here. So now this is going to work out to, we have -4 plus 2, and -4 plus 2 simplifies to -2. And then we have 4 minus -3 changes to 4 plus 3, which is 7. So there's the slope that we need. And remember, the slopes of parallel lines are equal. So the slope that we need is -2/7, but we have to be careful here. In this case, we're going to be writing the equation of a line going through the point 3, 2. Some students might fall in the trap of using the point -3, -2, since it already says x1, y1. But remember, when you're using the point slope form equation, you're going to be using the point that you want to pass through as your x1, y1. So in a sense, like these labels get erased and they go away. And now we're plugging into this formula here. So I'm just going to go ahead and erase this so that it's out of the way and it's not confusing to what we're actually trying to find here. So now we plug in, we have y minus, the y value here is 2, equals, the slope is -2/7. And now we have x minus 3. And here's our solution. We don't actually have to solve this and write it in the form y equals mx plus b. We could stop at this step. If you want to solve it out from this step, you can. But once again, you're not going to get any extra points. But if you just want to see how this is done, we have -2/7 times x. And then we have -2/7 times -3. So what I'm thinking about here, I'm doing 2/7 times 3. I just multiply 2 times 3 is 6. So I get 6/7. We have a negative times a negative is a positive. So we get plus 6/7 like this. And now I have y minus. And what I would want to do here, all in the same thought, is I would want to write 2/1 like this. And I would want a denominator of 7. So I multiply by 7/7. And that gives me 14/7. So I would have y minus 14/7, and if I want to solve this for y equals, I just add 14/7 to both sides. Okay, so I would have this, and now this will cancel out, and we'll have y equals -2/7 x plus 20/7 after we do 6 plus 14. So this would also get you full credit, but once again, it's not worth the risk. And now graphing this to check our answer is not going to be polite because notice 20/7 is almost 3, but it's a really wacky decimal. And then we have to go down 2/7 from that location. So graphing this, once again, it's not going to be super helpful here. It'll give us an idea if our answer is correct. But because these are not nice numbers, I would just stop here and say that we're good. Question 32, we have this word problem here, and everything in this first part is transferred over to the diagram. We're in Florida, NASA is launching rockets into space, and we're told that a person is viewing the launch of the rocket from this point here, over at point A. And they are 3,280 feet away from point B, which is the launch pad. And the person observes the rocket go up, and at point C, when the rocket is this high up, the angle of elevation is 15 degrees. And then a moment later, when the rocket is up here at point D, the angle of elevation is 31 degrees. And now for the actual question, we have to determine and state to the nearest foot the distance the rocket travels between the 2 points C and D. So what we're basically finding in this question is what is the length of this segment? So for this question here, I like to draw out 2 separate triangles. So we have this right triangle here, and this represents the small right triangle where we have a 15-degree angle over here like this. The distance is 3,280, and then this vertical distance here, I'm just going to call this x for now. And then a moment later, we have the big right triangle, and that's for the second angle of elevation. So that's when we have an angle of elevation of 31 degrees. So we have 31 degrees here like this. And then we have, this is still 3,280 because the person is not moving. They are the same distance away from the launch pad throughout the rocket launch. So now we could just use trig to find out what is the value of x, and we'll call this one here y. So remember SOHCAHTOA. Okay, this helps us choose the correct trig function to find the missing part of the triangle here. So what I'm looking at is there's our 15-degree angle, and this is the side opposite, and we know the adjacent side. So when you hear opposite adjacent, you should be thinking of tangent. So I could say here tangent of the angle, and the angle is 15 degrees, is equal to the side opposite, which is x, over the adjacent side is 3,280. So to solve for x, all I have to do here is cross multiply, and I'm going to have x times 1 is x, and that's going to be equal to 3,280 times tangent of 15 degrees. So now we just type this in, and remember, we're in degree mode here. So we have 3,280, and we're multiplying by tangent of 15 degrees, and that gives us this value here. Now, one thing I want to emphasize is they did tell us to round to the nearest foot, but you should only be rounding at the very last step, because if you round at every step throughout the question, this can throw your answer off by a little bit, and that's an annoying point to lose on a test like this. So we have 878 point, and we have 873, and then we have 3512. So once again, I'm writing out all the decimal places, and I'll round at the last step. So now for the second triangle, we have y is opposite of the 31-degree angle. So this is the opposite side. And then this side here, 3,280, is adjacent to the 31-degree angle. So once again, we're going to be using tangent. And this time around, we're going to have tangent of 31 degrees is equal to the side opposite is y over the adjacent side is 3,280. So now same technique, we're going to cross multiply. And now the second time around, we're going to have y equals, and we have 3,280 times tangent of 31 degrees. So just to save time, I'm going to go up to this and press enter, and I'm just going to change the angle here to 31. So now for our second side, we have this value. So y is equal to, and we'll write a few decimal places. We have 1970 point, we have 82283. But remember, our goal is to find the distance between these 2 points here. And if you just know to subtract these two numbers, then great. Otherwise, what you could do is you could call this z, since x and y are already taken. And then this distance we labeled as x. And we called this big distance from here to here, we called it y. So if we want to come up with an equation here to connect these, we could say that x plus z is equal to y. And then if we want to actually solve for z, all we have to do is subtract x on both sides. So we're going to have z is equal to y minus x. So if we want to find out what is the value of z, now we just subtract. So we're going to have this value here. I just press enter, subtract, and we have this value here. I'm just going to go up to it and press enter. And now we press enter one more time, and here's the distance we want. Now remember, we're going to round our answer to the nearest foot. So we look at the ones place here as a 1, and then we go to the right is a 9. So we're going to round this up to 1,092. And remember, for the regions, we don't get penalized for not writing units in. So we could just say 1,092. Question 33, we have a small can of soup is a right circular cylinder with a base diameter of 7 centimeters and a height of 9 centimeters. Then we have a large container is also a right circular cylinder with a base diameter of 9 centimeters and a height of 13 centimeters. And now for the actual question, we have to determine and state the volume of the small can and the volume of the large container to the nearest cubic centimeter. So for this question, we have to know this formula. We have V equals pi r squared times h. And if we forget this formula, it's on the back of the test on the reference page. But what we have for the small can here, so let's take a look at the small can. So there's the small can, and we're told here, so not necessarily drawn to scale, but there's the can, and we're told that the diameter is 7 centimeters. And just know the base diameter here at the bottom is the same as the diameter at the top. So that part doesn't matter, but be careful here. Don't do something like pi times 7 squared. Okay, this is a very dangerous bear trap. Students will sometimes just plug right into the formula right away, but you have to find the radius first, and that you would get from dividing the diameter by 2. You would get the radius is 3.5 centimeters, and that's the distance going from the center here across like this. That's the 3.5 centimeters. All right, and now the height here they told us was equal to 9 centimeters, and that's the distance going from the top circle here at the center all the way to the bottom like this at the center over here, and we're told once again the height is 9 centimeters. So now to find the volume of the small container, all we're going to do is plug this stuff into the formula. We're going to have pi times the radius is 3.5 centimeters, and that's being squared, and the height is 9 centimeters. Now, I'm actually including the units this time because for this math test, you're not graded on units, but just know when you take classes like physics or any other class where math is applied, the units all of a sudden do matter, so why not practice how to write units in the question? So you could see here, if I did centimeters squared, that's square centimeters. And if I do square centimeter times centimeter, that would give me cubic centimeter. Okay, so that's how I know the units are going to match out here. So the volume of the small container, we could just type in now, we're going to have pi times, we have 3.5 squared. and then we're multiplying that by 9. Okay, so we just throw in our parentheses and our 9, we press enter, and here's our solution. So we're rounding to the nearest whole number here. So we look at the ones place as a 6, we look to the right as a 3, so we're going to round down, we're going to have 346, and the units here are cubic centimeters, so I write centimeters to the third power, and here's the volume of the small container. So now for the large cylinder, we have the diameter is 9 centimeters, and we were told the height is 13 centimeters. So we still have to find the radius. The radius we're going to get by dividing the diameter by 2, and we're going to get 9 divided by 2 is 4.5. So the radius is 4.5 centimeters. So there's our large cylinder. I'll draw it over here, and not necessarily drawn to scale, but there's our cylinder. All right, and we're told here the radius is 4.5 centimeters. So that's the distance from here to here. 4.5 centimeters, and the height is the distance going from the top circle center to the bottom circle center is 13 centimeters. So now the volume of the large container, we'll just label that as volume of the large, writing this as a subscript, is equal to pi times the radius is 4.5 centimeters, and we're squaring it, and we're multiplying that by the height, which is 13 centimeters. So now just to save time here, remember our radius was 4.5, so I'm just going to go up to the 3 and make it a 4, and we're multiplying at the end by 13 instead of 9. So I just put a 13 and close the parentheses, and here's the volume of the large container. So once again, we're rounding to the nearest whole number, so we look at the ones place as a 7, and to the right we have a 0. So this tells us that the volume of the large container to the nearest cubic centimeter is going to be 827, we have cubic centimeters, and here's the volume of the large container. So now for the last part of this question, what is the minimum number of small cans that must be opened to fill the large container? And we have to justify our answer, which just means we have to show the math. So what I'm thinking about here is we have the small containers, and they have 346 cubic centimeters of space. And let's say we need X of them to fill up the large container, which has 827 cubic centimeters of space. So to find out how many number of cans X we need, we divide both sides by 346. So the actual work that we show, the justification, is we're going to do 827 divided by 346. So let's go ahead and do that. We have 827, and we're dividing by 346. So now we can record the number. We have 2.39017,341. And they want to know, what is the minimum number of small cans? So we look to the ones place, and to the right is a 3. So we should round down to 2. But no, this is a very, very, very dangerous bear trap. They're not telling us to round to the nearest whole number. They want to know, what is the minimum number of small cans? And in this case, it's going to be 3. So what you want to be thinking about here is that a small can has 346 cubic centimeters of space. And if we do 346 plus 346, if we only had 2 cans, and you add this up here, so let's work this out. This would work out to 692. So 2 cans only has 692 cubic centimeters of stuff in it, of soup, and that would not fill this because 692 is less than this. But if you did a third can, so we add another 346, so a third small can here, this one works out after we do the addition to 1038, which is greater than 827. So that's why here we're going to need 3 small cans. Okay, so what is the minimum number? We're going to say 3 small cans, and we only have to justify our answer, which just means we have to show the work, which we did. Question 34, we have parallelogram math with these vertices here, and we want to prove that this parallelogram is a rhombus. So what I'm thinking about here is I want to show that all 4 sides are equal in length, because I know that a rhombus is a quadrilateral where all 4 sides are equal. So I think the easiest way to prove that something is a rhombus is to find the distance between all of these points and to show that all 4 of those side lengths are exactly the same. Okay, so this is not necessarily drawn to scale. So we're going to be finding the length of side MA, we're going to be finding the length of side AT, and then we're going to be finding the length of the other 2 sides here. So we have the length of side TH, and then we have the length of side MH. All right, so these are the 4 distances we want to find. Now, if you have the distance formula, you could just use it 4 times. Otherwise, you could just plot all 4 of these points. So now to find these 4 sidelines, what we could do is we could draw in these vertical and horizontal lines. So I'm going to draw up a vertical line here from M going up to A. So I'm going to go up to this location, and I'm going to go across here so that I get from M to A. And then think about, how much do I have to go up and over? I have to go up 1, 2, 3, 4, 5, 6. So I'll label that here. We're going up 6, and we're going over 1, 2, 3, 4, 5, 6, 7. So we're going up 6 over 7. And now how do we get from A to H if we're going to the left, right, up, and down? We're going to go across this much here, and then we're going to drop down this little amount here to build another right triangle. So we're going over 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're going across 9, and we're going down 2. And then I do this for the other ones here. So from T to H, I'm going to go down to this location here. So I'm dropping down to -4 on the y-axis, and I'm going across this distance. So now I could just count the rise over run again. I'm going to be going down 1, 2, 3, 4, 5, 6, and I'm going across 1, 2, 3, 4, 5, 6, 7. And then for the last one here, you could see that the numbers are matching. I'm going to guess that we're going to be going across 9 and up 2, but if we want to be 100% sure here, we just draw in the lines. And now we could count that we're going across, we're going 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is 9. And then we're going up 1, 2 like this. So now we could use the Pythagorean theorem. So the Pythagorean theorem tells us when we have a right triangle, we could say that a squared plus b squared equals c squared, where a and b are the lengths of the legs and c is the length of the hypotenuse. So one thing you could do all in one shot is you could solve for c. You could take the square root of both sides, and that'll tell you that c is equal to the square root of a squared plus b squared. So if I want to use this formula, let's say to find ma, notice that ma is built with this right triangle here with the two legs that are 6 and 7. So what I could do is I could just do the square root of, and I would have 6 squared plus 7 squared. And now this simplifies to, we would have 36 plus 49. And if we add those two here, we're going to have the square root of 85. So that would be the length of MA. And now I'm going to use this formula again to find the length of AT. And notice that we're going across 9 and down 2 in this right triangle. So this time around, I would have the square root of, I would have 9 squared plus 2 squared like this. And that's going to give us, we're going to have 81 plus 4. And then that simplifies also to square root of 85. So this is looking good so far. So now TH is the distance from here to here, and that involves this right triangle. So we would have here, so let's just make that a little bit neater. So we have the square root of, we're going to have 6 squared plus 7 squared, which is the same thing as what we did in the first line here. So we're also going to have square root of 85. And now for the last one, for MH, we have a 9 and a 2 for those legs. So we're going to do the square root of 9 squared. So we'll make that a little neater, 9 squared plus 2 squared. And that also simplifies to square root of 85. So now we just have to write out our proof sentence here, and we could just comment here. Notice all 4 sides are equal in measure, so that makes all 4 sides congruent. So math is a rhombus because it has 4 congruent sides. Now, once again, to prove that this parallelogram is a rhombus, we just have to establish here that all 4 sides are congruent, and then that's enough to say that this is a rhombus. And one other thing here, this notation, the 3 dots in this triangular form here mean therefore, and that's just a nice way to abbreviate when you're writing proofs. So for the last part of this question, we're going to determine and state the area of MATH, which is the rhombus on the inside. So we're going to find the area of this big rectangle, and then we could subtract out the area of these 4 right triangles here. And that's just going to leave us with the area of the rhombus on the inside. So that's a nice way to do this question. There's more ways to do it, but I'm pretty sure this is the easiest way to do this. So what we have is we're going to have the area of MATH. So the area of MATH is equal to, we have the area of the big rectangle. And we just have to think about this. The big rectangle, if I expand it out like this, notice we're going across 7 plus 9, which is 16. And we're going down 2 plus 6, which is going to give us 8. So the area of the big rectangle is 16 times 8. And then we're going to subtract, we have to add up the area of the 4 right triangles like this. So we have 1/2, and conveniently, these are all right triangles, so we have the base and height. So remember, the area of a triangle is 1/2 base times height, so we have 1/2, and we'll start with this triangle here. We have 1/2 times, we have 7 times 6, and then we have the second right triangle is going to give us 1/2. We'll do this one next. We have 9 times 2, so we have 9 times 2. And then we have 1/2. The third right triangle down here is, once again, 7 times 6. So then we have the last one here, 1/2, and we'll make a little bit of space here. So for the last one, so we just did this third one here. The last one is another 2 by 9. So we have 1/2 times 2 times 9. And now we just type this in. So we could type this entire expression right in the calculator. We're going to do 16 times 8. And now we're subtracting, and we throw on a parenthesis here. And we have 1/2. I'm just going to write 0.5. So we have 0.5. And we're multiplying by 7 times 6. Let's pretend we don't know 7 times 6 is 42. So we'll just do all of this in the calculator. Then we have 1/2 times 9 times 2. So we're going to multiply that one out. And now we have the third triangle we said was 0.5 times 7 times 6. So we have, and let's write a plus here. So we have plus, we have 0.5 times 7 times 6. So that's our third triangle. And then the last one here, we have another plus 0.5 times, we have 2 times 9. Okay, now we could close the parentheses and press enter, and this gives us the area 68. So our solution here, the area of math is 68 square units. Question 35, the triangle proof. And the first thing I like to do for these questions is transfer the given information over to the diagram. So we have quadrilateral ABCD, and we're told that AB is congruent to CD. So I'm going to mark these off here with tick marks. And then we have that AB is parallel to CD. So we'll put arrows here to show that these are parallel. And then we have diagonal AC intersects EF at point G, and we have DE is congruent to BF. So I'm going to put marks over here to show that these segments are also congruent. And now the proof statement is we have to prove that G is the midpoint of EF. So we're trying to prove here that G is right in the middle of EF. So when I do these questions, I spend a lot of time thinking of strategies. So the proof here, once again, is to prove that G is the midpoint of EF. So what they're really asking us to do in the second to last line here is to show that EG, that segment, is congruent to FG. So that's what we have to show in order to establish that G is a midpoint. But then how do we show that line segments are congruent? Well, we show that they're parts of congruent triangles. So I'm looking here and saying, well, these triangles here would have to be congruent. That's going to be part of our strategy. So then I say, all right, I have to show that triangle AEG is congruent to triangle CFG. Okay, that's going to be part of my proof here. But now I think about how do I show that these two triangles are congruent? So now it's like starting to unravel more and more. And I think about what we have. So another thing that jumps out at me here, so another thing that I'm thinking about, so I'll put another thought bubble over here, is right away I could see that AB and CD are both parallel and congruent. And what that tells us here is that ABCD is a parallelogram. Okay, so ABCD is a parallelogram, once again, because it has one pair of opposite sides that are both parallel and congruent. And then once we know that this is a parallelogram, it's going to unlock a whole bunch of information. Well, for one, this doesn't matter that this is a parallelogram for this part, but when you have intersecting lines, the vertical angles formed are congruent. So this, we already have a pair of angles are the same. So in terms of how do I show that these two triangles are congruent, I have a pair of matching angles. And then I look here, if this is a parallelogram, notice I have alternate interior angles because I can show AD as parallel to BC. So I have alternate interior angles, so I could show that these angles here are also congruent. So far I have angle, angle. And then I think here, okay, I have to be able to show a pair of sides are the same. And think about, since we have a parallelogram here, we know that these opposite sides are going to be the same. So then I see here, if the opposite sides are the same and these two pieces are the same and I subtract them, that tells me that these segments AE and CF are going to be the same. So now I'm thinking angle, angle, side. So now we can start with our statements and reasons here. And the first thing you always have to write is the given information. You don't get any credit for just writing this, but you have to write it to get full credit. So for the next statement reason, we have flexibility in terms of what we could write next. But I'm going to say here that ABCD is a parallelogram. And remember, the reasoning is that we have one pair of opposite sides that are both parallel and congruent. So now once we establish that ABCD is a parallelogram, we could say that AD and BC are both parallel and congruent. Now, one small detail before we move on, we really have to establish here that AD is parallel to BC because otherwise we can't use alternate interior angles to show that these two angles are congruent. And just know that's a common detail that people leave out. They forget to say this. They just say that this is a parallelogram and then they go right to alternate interior angles. So just make sure that you establish that. So let's establish that these angles are congruent next. And I'm just going to go ahead and number them as angle 1 and angle 2 because that makes it easier to write out in the statement section here. So we could say that these angles are congruent because when parallel lines are cut by a transversal, alternate interior angles formed are congruent. So now one thing to be mindful of is we just established that we have a pair of angles congruent in these two triangles here. So one part of this is done. So now we move on to the next pair of angles. We could say here that angle 3 and angle 4 are congruent because vertical angles are congruent. So now we just established that another pair of angles are congruent. So the last thing we have to establish before we could say these two triangles are congruent is we have to establish that a pair of sides are congruent. And now my focus is over here on segment AE. We have to show that segment AE is congruent to segment CF. And think about what we had in the beginning. We were told that these little segments were congruent. And we also established in line 3, once we established that we had a parallelogram here, we said that the entire segment AD is congruent to the entire segment BC. So this is where the subtraction postulate comes in. If we know the entire segments here are congruent and the parts of them are congruent, then if we subtract here, the differences AE and CF have to be equal in measure. They have to be congruent. Now, one thing I want to point out here before we move on in the proof is that this statement, this part of the statement is optional. I don't have to write this, but the reason that I do is to show here what we have to establish before we use this subtraction postulate. Notice that we said that AD was congruent to BC in this step here. We said the entire segments were the same. And in statement 1, we said that the little parts here, DE and BF, were congruent. So once you make those two statements of congruence, the whole parts are congruent and the small parts are congruent, then you could use the subtraction postulate, which establishes here that AE is congruent to CF. So we just established a pair of sides are congruent in those two triangles. So now we could use AAS. And once we have the triangles established as congruent, then the corresponding parts of these congruent triangles are congruent. So now we'll continue here. We have for statement 8, we're going to say here finally that EG is congruent to FG because corresponding parts of congruent triangles are congruent. And now finally we can close out this proof. We're going to say here that G is the midpoint of segment EF because G separates EF into two congruent segments.